Hello, everyone. All right, we are continuing along with accumulation, and this builds off the discussion from last time where I gave you a graph and asked you to accumulate using areas of triangles and things, and then it was total distance. That's the third kind of piece to this. So the goal is to be able to, whether I give you a equation, whether I give you a table, or whether I give you a graph, you should be able to do these accumulation type things where you are finding information about the original function based on one of those three things as the derivative. So I give you the derivative as a table, derivative as an equation, or derivative as a graph, which is what we're doing today. So I would copy this graph down in your notes. Now, notice something. This graph is funny looking. It's not a smooth curve. It has cusps throughout. So I see a cusp here. I see a cusp here. They designed these problems, and I'm designing these problems, so that you can geometrically find the areas. That's why they look this way. If this was like a normal smooth curve, we wouldn't be able to find the area under it. We'd have to approximate the area under it. So we would be doing basically what we do with a table. So the reason we get such funny looking weird graphs that have these pointy cusps is because all of these are shapes that we can find the area of using geometry. So that's going to be the goal today. So I am going to give you an initial condition. We're going to call this the derivative graph. So this is the graph of f prime. We have our derivative graph. And notice it's going to be some combination typically of circles or semicircles or quarter circles and triangles. Typically, those are the shapes you're going to get. All right, and I'm going to start you from f of 0. So I'm going to tell you that f of 0 is equal to, let's just say 3. That's your initial condition. So right off the bat, make sure you understand what I'm saying. This is the derivative graph. So right away, we can kind of think about what the original function is doing by curve sketching. Look, we have all this positive area. So from 0 to, it looks like 6, the original graph should be going up. So from 0 to 6, the original function is increasing. And then from 6, well, I guess I should run it up more. From 0 to 6, the original function is increasing. Then from 6 to 9, the function's decreasing because we have negative area. And then from 9 to 10, the function's increasing. Obviously, I didn't do anything with concavity, but that's the general shape of what the original function should be doing. Going up, going down for a little bit, and going back up. That'll be helpful when we start finding these values. So first value I want to find is this one right here, f of 3. What's going on in the original function at f of 3? So here's how you do it. The setup looks exactly the same. So to find f of 3, we are still going to set up our initial condition plus accumulation. Initial condition plus accumulation. I really hope you're getting tired of hearing that. If so, then I'm doing a good job because it is such a crucial calculation. So the initial condition is our initial condition, f of 0. And the bounds, and this is going to be important for later, should be from where you're at to where you're trying to get. You are accumulating a rate from 0 to 3 of your derivative graph. So that when you do the fundamental theorem of calculus, the integral of the derivative cancels, and you'll be left with f of 0 plus, and then this piece right here, if you think about it, which we've been flirting around with this idea, the antiderivative of the derivative just gives you f of 3 top bound minus bottom bound. And then notice if I do f of 0 plus f of 3 minus f of 0, we're left with just f of 3. So that's why this calculation works the way it does, because of the fundamental theorem of calculus. All right, so we know f of 0. F of 0 is our initial condition. But how do we get this accumulation component in this situation? Next class, I will really stress the ways to get this. But when I'm given a graph, in this case, you're going to have to find the area using geometry of some type. Oftentimes there will be a semicircle, so you need to know the formula to find the area of a semicircle or quarter circle. So in this case, it is 3 plus. I like to shade in what we're finding. So we're calculating this area under the function to accumulate the total. This is a quarter circle, so it's 1/4 quarter circle of, and the formula for a circle, by the way, in case you didn't know, area is equal to pi r squared. So a quarter circle is just a quarter of that. So pi, and in this case, what is the radius? It's the distance from the center out. It's 3. So in this case, it would be 9. And yes, I will take this answer. 3 plus 9 pi over 4. That is f of 3. You're going to get answers like that are not pretty because they're combinations of numbers and pi's. But that's fine. We'll just carry it with us and continue on. So the next value I want to get is our maximum, which is at 6. So to get f of 6, you can either start from the beginning, f of 0, and add all the accumulation, but I like working my way along the graph. That's what I have you doing in the discussion. I'm going to work my way along the graph. So I'm going to start at f of 3, because I just found that value, and I'm going to add the accumulation from 3 to 6 of the area under the derivative curve, which gives me whatever the area of this component is. That is a triangle. So it's 3 plus 9 pi over 4. That was our initial condition. Plus, we need the area of this triangle. Well, the area of a triangle is equal to 1/2 base times height. The base of this triangle is 3. The height of the triangle is 3. So it's 9/2. And if we add 3 is the same as 6/2. 6/2 plus 9/2 is 15/2 plus 9 pi over 4. Typically, I keep the pi term and the non-pi term separate. You can plug in your calculator and get an actual answer using decimals, but I like pi's and non-pi's. Just keep it going. All right, continuing this logic, let's get to our next spot that we can find fairly nicely. I could try to find f of 8, but why not just go all the way to f of 9 and find the area of this triangle? It's not a right triangle, but our calculation for triangle will still work. So to get f of 9, we're going to use f of 6 plus the accumulation from 6 to 9 of our derivative graph, which is 15/2 plus 9 pi over 4 plus accumulation. In this case, we have a triangle, so we're accumulating this area. But remember, we're going down here because we have negative area. So you got to remember that anytime your graph is below the x-axis, your derivative graph, that's negative area, meaning we're going down in the original function. So this value needs to be negative once I find it. And it looks like it's a base of 3, a height of 2. So 3 times 2 is 6, divided by 2 is 3. But remember, negative 3, because we're going down, negative area. We're below the x-axis, we're accumulating negative area. So 15/2, 3 is the same as, what, negative 6/2. So 15/2 minus 6/2 is 9/2 plus 9 pi over 4. There we go. And lastly, if I really wanted to, I could go all the way to f of 10. So that was kind of my goal, was to get to f of 10. So f of 10, we're trying to get here. We have this area. We take f of 9 plus the accumulation from 9 to 10. And that is 9/2 plus 9 pi over 4 plus the accumulation. It's positive and it's a triangle. Half base times height, so 1/2, 1 times 2, which is 1. And that looks like we get 11/2 plus 9 pi over 4. And that is our final value for 10. Okay, so that's how you accumulate with a graph. If I give you a graph, and it's a bunch, if I don't give you an equation, so I mean, we're going to see if I give you an equation and a graph, that's even better because you can use the equation. But if I give you a graph with no equation, chances are you're going to be able to find the areas, or you'd have to do a Riemann sum. So there's lots of different situations. You have to know which tool to use. So next class, I will really lock in the different examples. because you have to know what strategy to use depending on what type of equation you've been given. All right, and then just keep going along your way. So I can find the area of this quarter circle. I found the area of this triangle. I found the area of this triangle. I found the area of this triangle. Oftentimes, when we start getting to the FRQs, I'll tell you to do all this at once. In other words, I'll say something like, list every single one of these right off the bat. So we found that this area was 9 pi over 4. We found that this area was 9 halves. We found that this area was -3, and we found that this area was 2. I like to plug them in straight to the graph. That way, if I really wanted to, if I wanted to get right to the bat, like right to the point of the problem, f of 10, it would have been f of 0 plus the accumulation from 0 to 10. I could have done it all in one move if I didn't need to find all those points. So f of 0 was my initial condition plus the accumulation. Then it's just add up all these. 9 pi over 4 plus 9 halves minus 3, it's a negative area, plus 2. It's a little bit faster. You can do it all at one time. I mean, it's the same thing that we did. We 3 plus 9 pi, or 9 pi over 4 plus 9 halves minus 3 plus, oops, I said 2, but it's 1. 1. 1. And then you can get the answer. So that's accumulation with a graph. All right, let's do one more problem. And then for the discussion, you're actually going to put these two topics together. So the other thing, this is accumulating backwards. So I'm going to give you a function, a derivative. Remember, derivative and velocity are the same. So a lot of times I'll do these problems with velocity and ask for position. Or I can just give you the derivative curve and ask you for the original function information. All right, so this time I will have Desmos to help me out. So here we go. I'm going to give you the derivative. So let's say I gave you the derivative function. I said, okay, here's your derivative equation this time. 1/2 x plus 2 times x times, that's an x. I guess I should do it in the right order. Let's fix that. So 1/2 x times x plus 2 times x minus 4. I'm giving you the derivative, okay? Now in Desmos, you can't plug in derivative because it doesn't like that notation. You can't define a function as a derivative function. So I kind of will use different strategies. You'll see me calling different functions different things. One strategy might just be to call it f of x and remember that you're dealing with the derivative. Others might be to call it b of x, that means derivative function. I don't know. You're going to have to design a style that makes sense to you. For this one, I'll call it d of x. So I'll just say like, okay, this is also known as d of x in Desmos. Okay, I'm just using the letter d to remind myself that I have the derivative function graphed. All right, so in this problem, take a look at where my critical points are. -2, 0, and 4. That means the original function. If we were to just talk about what it's doing over time, it goes down, down until -2. At -2, it starts going up. At 0, it starts going down again. And at 4, it starts going up. It's a 4th degree, which makes sense because this is a 3rd degree. Okay, so we could have done it on top of here to be a little more precise. But remember what the shape should look like. So it doesn't have to be perfect, but right here, this was -2, this was 0, this was 4. Because, get ready for this, now we're going to start going backwards. So let's say I told you the initial condition was f of 5 equals 3. We are going to find f of 4 first. All right, so this is what I like to call accumulating backwards. We're going backwards. Basically, I'm starting you at the end and we're going backwards. We're going from right to left. We are accumulating backwards. We haven't seen this yet. How is this going to work? It's exactly the same. So pay careful attention. F of 4 to get f of 4, you have your initial condition plus accumulation. Initial condition was f of 5. Now this is the part you're going to be a little unusual with for a while. It's still plus. That's why I'm very emphatic about saying initial condition plus accumulation. Where are we starting? We are starting at 5. Where are we getting? We're trying to get to 4. These bounds are backwards. These bounds are backwards. Is that okay? Let's find out. So I can do the initial condition, which is 3, plus the accumulation, so int, from 5 to 4 of my derivative function, which I call d of x. And let's see where I ended up. Well, I better have been going down because f of 5 was up here at 3. So yes, negative 4.719 is a logical answer. It makes sense that my answer should be less. I ask you that all the time. Does your answer make sense? And yeah, it does. We should have been going down because from 4 to 5, we went up. So we're going backwards. Okay, so here's the thing you got to take away from this though. Typically, when these bounds are out of order, it works okay when you have an equation, but these bounds being backwards, this is a problem for tables, if we're trying to do this with a table or with a graph. So if you try to accumulate with the bounds flipped, it's harder to do. Like, it doesn't quite make sense. You have to almost accumulate backwards, which is weird. There's a fix for this, right? And I'm going to show you the fix right now. The fix is this. You are allowed to flip the bounds. We can literally take the bounds and flip them so that they are in the correct order. We want the bottom one to be less than the top. We want to accumulate from left to right. But you have to do something. You have to flip the sign in front. So flipping the bounds flips the sign of the integral. That's the key takeaway about accumulating backwards. And if you don't believe me, we can always go back to Desmos and do 3 minus int 4 to 5 e of x. Yes, same answer. Cool. So the story here is if you're accumulating backwards, still do initial condition plus accumulation. But think about it, if I'm going backwards, I'm subtracting area I accumulated. That's why we're allowed to do this flip. We're subtracting accumulated area. So let's continue on. This time we'll do it all in one move. That's the cool thing about using antiderivatives and actually having an equation. If I wanted you to find, let's say, f of 0. Find f of 0, use your initial condition, f of 5, plus accumulation from 5 to 0, derivative dx. Now that's fine, Desmos likes that. However, start realizing that that's logically a little weird. The bound should be from left to right. So you're subtracting accumulated area, and then you can find the area from left to right. So either one of these calculations will work in Desmos. But when you're doing it like on the discussion, flip the bounds and make it negative, and then find the area like normal. So positive area will be positive, negative area will be negative, just like I did earlier. All right, so either one of these is fine. If we go back to Desmos and we plug in from 5 to 0, or 0, 16.542. Yeah, and does that make sense in terms of where 0 should be? Yes. It's the max. 0 is the max. We went from a positive to a negative on the derivative graph. Okay. So, yes, it makes sense. It makes sense. And we can just keep going. So that's the idea. I mean, one more if you wanted to do one more and find f of negative 3, for example. Same thing. You don't even have to worry. F of 5 plus accumulation from 5 to negative 3. f prime of x dx. Flip the bounds or don't. Yes, get used to flipping the bounds, but for today, like I keep saying, it doesn't really matter. Desmos doesn't care if your bounds are wrong, in the wrong order. It accumulates based purely on computation. So it just literally does what it's been doing. But when you do it with a graph, which you're going to try in the discussion, you have to be very careful. And 17, does that make sense for where -3 is? Yeah, I mean, it's way up here. So yes, it makes sense. All those values tend to line up. One strategy that well, no, I won't get to that right now. I'm tempted, but no, we won't do that. So just one more thing, going back to this one. If you were to try to do this with a graph, let's say I gave you f of, so we'll do this. Let's say I gave you f of 10 was 5. And I would like you to find f of 6. Well, let's get to f of, I guess we could do it all in one move. Let's try it. Let's see if we can do it in one move. So f of 6 equals the accumulation, or initial condition, plus accumulation. My initial condition is f of 10, which means my accumulation needs to be from 10 to 6. But this makes no sense because we're not used to accumulating right to left. We need to accumulate left to right. So that is the same as f of 10 minus, we're accumulating backwards, and you can flip the bounds. And now, be very careful, 5 minus, and I would throw all of these in parentheses. This area was 1 for this little triangle here, so that doesn't change. Plus, this area, -3, was negative. So 5 minus 1 plus -3. So 1 minus 3 is -2. And 5 minus -2 is 7. So f of 6 is 7. Does that make sense? I mean, yeah, if you went back and forward way and tried it with f of 6, it's 7, and then checked your answer, 7 plus we have a -3 plus a +1. 7 minus 3 is 4. 4 plus 1 is 5. So we got back to where we started. So sometimes it's a good idea to check your answer by doing it forward. Make sure you matched up with all these negatives. This is what I mean in the discussion by sometimes negatives become an issue. If it's below the x-axis, it is always negative area. But you got to remember whether you are accumulating backwards. In this case, we subtracted negative area. A little tricky. All right, so do your best with the homework and the discussion. Next class, we will look at 3 examples of each type. One with a function, one like an actual equation, one with a table, and one with a graph. All right.